Hi everyone. We welcome you back to our next session, and this session is about the three-phase circuit analysis. I'm Amelia from I Teach You. Similarly, if you are not yet subscribed our YouTube channel, this is the time, and remember to like our tutorials too, since your subscriptions and likes encourage us to prepare lessons for your thorough understanding. The electrical system is of two types. In an example, the single-phase system and the three-phase system. The single-phase system has only one phase wire and one return wire, or in common words, live wire, and the neutral wire. Thus it is used for low-power transmission. The three-phase system has three live wires and one return path. The three-phase system is used for transmitting a large amount of power. The three-phase system is divided mainly into two types. One is balanced three-phase system and another one is unbalanced three-phase system. Herewith keep this in your mind, that any unbalanced system can be split up into a series of balanced systems. The balanced system is one in which the load is equally distributed in all the three phases of the system. The magnitude of voltage remains same in all the three phases, and it is separated by an angle of 120. In unbalanced system, the magnitude of voltage in all the three phases becomes different. The system which has three phases, in an example, the current will pass through the three wires, and there will be one neutral wire for passing the fault current to the earth, is known as the three-phase system. In other words, the system which uses three wires for generation, transmission and distribution is known as the three-phase system. The three-phase system is also used as a single-phase system if one of their phase and the neutral wire is taken out from it. The sum of the line currents in the three-phase system is equal to 0, and their phases are differentiated at an angle of 120 degrees. The three-phase system has four wire, in an example the three current-carrying conductors and the one neutral. The cross-section area of the neutral conductor is half of the live wire. The current in the neutral wire is equal to the sum of the line current of the three wires, and consequently equal to square root 3 times the zero-phase sequence components of current. The three-phase system has several advantages, like it requires fewer conductors as compared to the single-phase system. It also gives the continuous supply to the load. The three-phase system has higher efficiency and minimum losses. The three-phase system induces in the generator, which gives the three-phase voltage of equal magnitude and frequency. It provides an uninterruptible power. In an example, if one phase of the system is disturbed, then the remaining two phases of the system continue supplies the power. The magnitude of the current in one phase is equal to the sum of the current in the other two phases of the system. Let me ask you a question. Have you ever thought, why do we use three-phase systems? Number 1, because it can produce a rotating magnetic field. Number 2, because for the same size three-phase generator produces more power than single-phase generator. Number 3, because three-phase lines transmit more power. For example, uniform power transmission and less vibration in three-phase machines. Instantaneous power in a three-phase system can be constant, not pulsating. Number 4, because three-phase lines are reliable and more economical than single-phase, less amount of wires required. In a three-phase AC generator, there are three windings. Each winding has two terminals, start and finish. If a separate load is connected across each phase winding as shown in the figures here, then each phase supplies as independent load through a pair of wires. Thus, 6 wires will be required to connect the load to a generator. This will make the whole system complicated and costly. In a three-phase AC generator, there are 3 windings. Each winding has 2 terminals, start and finish. If a separate load is connected across each phase winding as shown in the figure below, then each phase supplies as independent load through a pair of wires. Thus, 6 wires will be required to connect the load to a generator. This will make the whole system complicated and costly. Therefore, in order to reduce the number of line conductors, the three-phase windings of an AC generator are interconnected. The interconnection of the windings of a three-phase system can be done in following two ways: star or Y connection and mesh or delta connection. The generated voltages VA, VB and VC, 120 apart from each other, are as shown in the graph. As you are aware, to transmit power with single-phase alternating current, we need two wires: live wire and neutral. However, you would have seen that distribution lines usually have only 4 wires. This is because distribution is done using three-phase and the fourth wire is the neutral. How does this help? Since the three phases are usually 120 degrees out of phase, their phasor addition will be 0 if the supply is balanced. It is seen from Figure 1, that in the balanced system shown, the three phases, usually designated R, Y, B corresponding to red, yellow and blue, are equal in magnitude and differ in phase angle by 120. The corresponding phasor diagram is shown in Figure 1b. The voltage between any of the phases and the neutral is called the phase-to-neutral voltage or phase voltage Vp. It is usual to call the voltage between any two lines as the line-to-line voltage or line voltage. BL. If the R phase voltage is VR equals Vp angle 0, then the remaining phase voltages would be Vy equals Vp angle plus 120 and Vbe equals Vp angle plus 240 degrees. The 120 phase difference of the three phases is a must for the proper working of the system. Otherwise, the system becomes damaged. However, the phase sequence is an important factor that we should be considered, and counterclockwise rotation is referred to as the positive sequence, where the clockwise is referred as the negative. For your reference, please give your attention into the figures provided. The three-phase systems are connected in two ways, in an example the star connection and the delta connection. The star connection requires 4 wires in which there are 3 phase conductors and 1 neutral conductor. Such type of connection is mainly used for long-distance transmission because it has a neutral point. The neutral point passes the unbalanced current to the earth and hence make the system balance. The delta connection has 3 wires, and there is a no neutral point. The line voltage of the delta connection is equal to the phase voltage. A balanced three-phase supply can be connected either in star as in Figure 2, or in delta as in Figure 2b. In a balanced three-phase system, knowledge of one of the phases gives the other two phases directly. However, this is not the case for an unbalanced supply. In a star-connected supply, it can be seen that the line current or current in the line is equal to the phase current or current in a phase. However, the line voltage is not equal to the phase voltage. The line voltages are defined as VRY equals VR minus VY, VYBE equals VY minus VB, and VBR equals VB minus VR. Figure 3 shows how the line voltage may be obtained using the normal parallelogram addition. It can also be seen that triangular addition also gives the same result faster. For a balanced system, the angles between the phases is 120 and the magnitudes are all equal. Thus the line voltages would be 30 leading the nearest phase voltage. Calculation will easily show that the magnitude of the line voltage is square root 3 times the phase voltage. IL equals IP. VL equals square root 3 VP. IL equals square root 3 ID. Similarly, in the case of a delta-connected supply, the current in the line is square root 3 times the current in the delta. It is important to note that the three line voltages in a balanced three-phase supply is also 120 out of phase, and for this purpose, the line voltages must be specified in a sequential manner. For example, VRY, VYB and VBR. Note VBY is 180 out of phase with VYB, so that the corresponding angles, if this is chosen, may appear to be 60 rather than 120. Thus, if the direction of VR is selected as reference, then VR equals VP angle of 0, VY equals VP angle of minus 2 pi over 3, and VB equals VP angle of minus 4 pi over 3, and VRY equals square root 3 VP angle of pi over 6, VYB equals square root 3 VP angle of pi over 2, and VBR equals square root 3 VP angle of minus 7 pi over 6. Balanced load. A balanced load would have the impedances of the three-phase equal in magnitude and in phase. Although the three phases would have the phase angles differing by 120 in a balanced supply, the current in each phase would also have phase angles differing by 120 with balanced currents. Thus, if the current is lagging, or leading, the corresponding voltage by a particular angle in one phase, then it would lag, or lead, by the same angle in the other two phases as well. Figure 4. The balanced load can take one of two configurations: star connection, or delta connection. For the same load, star-connected the impedance and the delta-connected impedance will not have the same value. However, in both cases, each of the three phase will have the same impedance as shown in figures 4b and 4c. It can be shown, for a balanced load, using the star-delta transformation or otherwise, that the equivalent delta-connected impedance is 3 times that of the star-connected impedance. The phase angle of the impedance is the same in both cases. ZD equals 3ZS. Note, this can also be remembered in this manner. In the delta, the voltage is square root 3 times larger and the current square root 3 times smaller, giving the impedance 3 times larger. It is also seen that the equivalent power is unaffected by this transformation. Three-phase power. In the case of single phase, we learned that the active power is given by P equals VI cos phi. In the case of three-phase, obviously this must apply for each of the three phases. Thus P equals 3 VPIP cos phi. However, in the case of three-phase, the neutral may not always be available for us to measure the phase voltage. Also, in the case of a delta, the phase current would actually be the current inside the delta, which may also not be directly available. It is usual practice to express the power associated with three-phase in terms of the line quantities. Thus we will first consider the star-connected load and the delta-connected load independently. For a balanced star-connected load with line voltage VL and line current IL, V star equals VL over square root 3, I star equals IL. Z star equals V star over I star equals VL over square root 3 IL. S star equals 3 volts star I star asterisk equals square root 3 VL asterisk. Thus P star equals square root 3 VL IL cos phi, Q star equals square root 3 VL IL sin phi. For a balanced delta-connected load with line voltage V line and line current I line, V delta equals VL, I delta equals IL over square root 3. Z delta equals V delta over I delta equals square root 3 VL over IL. S delta equals 3 V delta I delta equals square root 3 VL IL. Thus P star equals square root 3 VL IL cos phi, Q star equals square root 3 VL IL sin phi. It is worth noting here that although the currents and voltages inside the star-connected load and the delta-connected loads are different, the expressions for apparent power, active power and reactive power are the same for both types of loads when expressed in terms of the line quantities. Thus for a three-phase system, in fact we do not even have to know whether it is a load or not, or whether it is star-connected or delta-connected. Apparent power S equals square root 3 VLIL. Active power P equals square root 3 VLIL cos phi. Reactive power Q equals square root 3 VLIL sin phi. Analysis of three-phase balanced systems. Since we know that the three phases are balanced and that the voltages and currents are related to each other by 120, we do not have to do calculations for each of the three phases unnecessarily. We could calculate for just one phase, usually the A phase in a system with phase sequence ABC. There are two common methods of doing this. See the figure 5. A single circuit of a three-phase system. Consider the three-phase three-wire system shown in figure 5 with the neutral wire absent. For a balanced system, the supply voltages EY and EB will be 120 out of phase. Using Millman's theorem, or otherwise, it can be easily seen that the potential of the star point S of the load is equal to the potential of the neutral N of the supply. Thus whether neutral wire is present or not in the system, the analysis of the system can be identical. Thus we will draw a neutral wire between S and N of zero impedance and do our analysis in that manner. Once the neutral wire is in place, and there is no potential difference between S and N, we could analyze only one single phase of the system, namely the A phase. This may be redrawn as in figure 6. In this case, the supply voltage EP is a phase voltage, the supply current is the phase current IP, the load voltage VP is a phase voltage and the power PP is the power is one phase. If we compare with the line quantities, we have EL equals square root 3 EP, IL equals iota P and PP equals P over 3. Usually, we are more interested in knowing the voltage and the power from practical considerations, rather than the current. For example, if I ask you the voltage and power rating of a bulb in your home, you would know it. However, if I asked you for the current taken by the bulb, you would normally not be aware of the value but would probably obtain it from the wattage and the voltage. The same is true in a large power system. Thus we would like to reformulate the problem so as to give the voltage and the power at the desired values, even at the expense of a wrong current. B. Equivalent circuit for three-phase balanced system. Consider multiplying the source voltage EP in figure 6 by square root 3. This would increase both the line current IP and the load voltage VP by a factor of square root 3. Since both the load voltage and the load current has increased by square root 3 times, the load power would increase square root 3 times square root 3 or 3 times. Thus we see that such a circuit, figure 7, would have all voltages corresponding to the line voltages, and all powers corresponding to the total three-phase powers as desired. The only quantity that would be in error is the line current, which would appear as a current square root 3 times too high. This circuit is known as the equivalent single-phase diagram and gives the voltage and power as for the three-phase system but with the current being in error by square root 3 times. Unbalanced three-phase systems. An unbalanced three-phase system is one which is not perfectly balanced. It may be caused by the supply being unbalanced, or more usually the load being unbalanced, or both. In such a case, knowledge of the currents or voltages in one phase does not tell us the currents or voltages in the other phases. Thus all phase quantities must be independently determined. Let us consider some of the common unbalanced situations to see how this may be done. Star-connected supply feeding a star-connected load. If Z neutral is considered zero, each individual phase current can be independently determined from the supply voltage in that phase and the impedance of that phase. Then the load voltages etc. can be determined. If there is a neutral impedance, then using Millman's theorem, we will first have to determine the voltage of the star point of the load with respect to the supply neutral, from which Vsn is known. Thus the load currents can be determined from. Hence, the remaining quantities can be determined. Next way is if the system is a 3-wire system, rather than a 4-wire system, the analysis is the same as if Z neutral were infinity, I. In example 1 over Z neutral equals 0. Thus again Millman's theorem is used to determine Vsn and the load currents are then determined. Delta connected supply feeding a star-connected load. If the supply was connected, not in star but in delta, figure 11, which is not the case in practice, then we would have to write the Kirchhoff's current law for the loops and solve as a normal circuit problem. When a delta-connected supply feeds a delta-connected load, figure 12, which is not usual, then the line voltages are known so that the currents inside the delta can be obtained directly from Ohm's law. The line currents can then be obtained by phasor summing of the currents inside the delta. The remaining variables are then obtained directly. Star-connected supply feeding a delta-connected load. When a star-connected supply feeds a delta-connected load, figure 13, then from the phase voltages the line voltages are known so that the currents inside the delta can be obtained directly from Ohm's law. The line currents can then be obtained by phasor summing of the currents inside the delta. The remaining variables are then obtained directly. Thus basically, any unbalanced system can be calculated using the basic network theorems. Phase sequence. Three-phase system of voltages, or currents, has a sequence, or order, in which the phases reach a particular position, for example, peak value. This is the natural sequence of the supply. According to usual notation, we would call the sequence RYB or ABC. If we consider a balanced system of voltages, or currents, they will have only the natural sequence, and there will no other components present. However, Fortescue has formulated that any unbalanced system can be split up into a series of balanced systems. This is like saying that any force can be broken up into its components along the x-axis, y-axis and z-axis. The advantage of such a decomposition is in the analysis of more than one quantity. If I repeat it, any force can be broken up into its components along the x-axis, y-axis and z-axis. I believe we learned a lot in this single video tutorial. And this is the time to review what we learned briefly. The conclusion. phase voltage is the voltage between the related phase and the neutral, and phase current is the current flowing through the related phase. In three-phase system, there are three phases instead of one phase as we see in the single-phase system, and each phase is separated by 120 degrees. For example, 360 degrees divided by 3 gives 120 degrees. In three-phase systems, there are mainly two configurations. Number 1 start or Y and number 2 delta or mesh. In star configuration, there is a neutral wire along with the other three-phase wires. But in delta, we meet only three-phase wires and no neutral. We are used to consider the phase which has the angle of 0 as the reference. We take our measurements in two separate ways. Number 1 either phase to neutral, or number 2 phase to phase, or well known as line to line. Phase to neutral means we will observe all our required reading between the related phase and with the neutral. Line to line means we will observe our readings between the related phase with the next phase. As we know, in most cases, the single-phase voltage is to be 230 volts and the summation of three-phase voltages would be 400 volts. How this happens? For example, as we now learned, in star configuration, the phase voltage can be taken if the line voltage is divided by square root 3. So in other words, if we multiply our single-phase voltage by square root 3, we can take up the line voltage. In a 230 V single-phase system, it is as follows. 230 times square root 3 equals 400 volts. Hence, in star configuration the phase voltage equals line voltage divided by square root 3. And phase current equals line current. But in delta configuration, the phase voltage and the line voltage is the same, where the phase current equals line current divided by square root 3. Now let's consider about the load connections with the sources. In most applications, loads are connected in star configuration for the purpose of connecting with the ground potential and to balance the voltage across each load. But in most industrial applications, delta configuration is used. Even though it doesn't have the access to ground or neutral, it gives a higher voltage across the load. The higher voltage means a lower current. There are 4 ways to connect the load with the source. Star to star, star to delta, delta to delta, delta to star. Mathematical calculations of star to star or delta to delta connections are not that complex. But when we came in to calculate either star to delta connection or delta to star connection, the complexity is higher and it is too complicated if we are going to build mathematical expressions for a circuit in 2 separate configurations. Thus, transforming into one relevant configuration, mostly into the source configuration, is the best way of solving these circuits. This situation is something like analyzing a circuit when the resistors are neither parallel nor in series. Hence it is proved that for delta to star conversion, each resistor in the star network is the product of the resistors in the 2 adjacent delta branches divided by the sum of the 3 delta resistors. Similarly, for star to delta conversion, each resistor in the delta network is the sum of all possible products of star resistors taken 2 at a time divided by the opposite star resistor. Therefore, if we consider the source or the load as a resistor, we are able to simply solve and build a mathematical expression for the circuit. Likewise, if I list you down, the steps of solving this type of questions are as follows. Step 1. Identify the configuration on the source side and the load side separately. Step 2. Transform the load side configuration into the source side configuration using the given transformation method herewith. Step 3. Draw the per-phase circuit diagram for any selected phase. Step 4. Build the mathematical relationships for the per-phase equivalency root. Step 5. Do the same for the rest. Take some time to read the following conclusions we have up to now been learned. So thank you for staying with us from the beginning, and we strongly believe that now you have able to gain your knowledge of 3-phase systems. If you have not yet been subscribed us, please subscribe and also give us a like if you are interested watching us further. Until we see you in another important tutorial, have an enjoyable time.